Hi, this is Stu Schwartz from MasterMathMentor.com. This is video BC Non-Essential 1a. The topic is the Epsilon-Delta definition of the limit, and it covers the BC manual pages 143 and 144. Back at the start of AP Calculus, we studied limits. We showed techniques to find them by simple arithmetic, and then by algebra, and then by using L'Hopital's rule with calculus. But we really never defined limits. What is a limit? In many cases, it is a hazy concept. Ask someone how much they might spend for a new car, and they might say that their limit is $30,000. Really? Suppose the car was $30,001. Would they buy it? Suppose it was $30,000.01. If the answers to these questions are yes, then $30,000 wasn't really their limit. Suppose you call a helpline and are told that the length of the wait to speak to someone is a certain amount of time. If you are told 1 minute, obviously you stay on the line. But if you are told 1 hour, you probably hang up. So what is the limit to how long you will wait? 10 minutes? If 10 minutes is your limit, how about 10 minutes and 1 second? If you say, yes, I would stay on the line for 10 minutes and 1 second, then 10 minutes wasn't really the limit. So if there is a limit, how do you find it? It's hazy. In calculus, we said that if f of x approaches some number L as x approaches c, then the limit of f of x as x approaches c is equal to L, and L is the limit. But what do we mean by approaching? Approaching is a relative term. In distance, a plane flying into Miami may be said to approaching the airport when it is 50 miles away. But when traveling by car, we might say that we are approaching home when we are a half-mile away. With time, it is approaching Christmas when we are a few days away from it. But yet, a football game is approaching its end when there are fewer than 30 seconds left. With price, the price of gas may be approaching its minimum price when it gets within a few cents of it, but the price of a new car might be approaching its minimum price when it gets a few $100s of it. In the mid-1800s, mathematician Augustine Cauchy developed a definition of the limit using the Greek lowercase letters epsilon and delta. His definition states that the limit of f of x as x approaches c is equal to L means that for any epsilon greater than 0, there exists some number delta such that f of c plus or minus delta will lie in the interval L minus epsilon, L plus epsilon. Or we can write the absolute value of f of x minus L is less than epsilon whenever the expression absolute value of x minus c is between 0 and delta, with x not equaling c. This probably makes no sense to you. We will see some examples of this in the next few slides and understand what it really means. So what does this mean? It is best explained using the figure on the screen. We draw the graph of f of x and choose some number L. We draw a horizontal line in red from y equals L to y equals f of x. And then we draw a vertical line from that point down to the x-axis, and we will call this number x equals c. Next, we choose some small number epsilon. We draw a horizontal line along L minus epsilon to f of x, and then a horizontal line along L plus epsilon to f of x. From those points, we draw vertical lines down to the x-axis. They will intersect the x-axis at c minus delta and c plus delta. So, when you choose an epsilon about L, you are in the edge of the light red rectangle. This will then correspond to a delta in the edge of the light green rectangle about C. As epsilon gets smaller, then delta gets smaller as well. And the gray rectangle at the intersection of the horizontal and vertical rectangles gets smaller as well, converging to the point CL, whether or not this point is actually on the curve f of x. The Cauchy definition can be used to actually find limits, but we would only do this if we wish to provide an extremely formal and rigorous proof. Our job is this. We will be given a function f of x, and the limit of f of x as x approaches c. You will also be given some epsilon, and from there we want to find the corresponding delta. Here is an example. If we were given that f of x equals 3x plus 2, and we know that the limit as x approaches 1 of f of x is equal to 5, we would like to find some positive value of delta such that the absolute value of f of x minus L is less than 0.01 when the absolute value of x minus 1 is less than delta. It sounds complicated, but we can see what we're trying to find by looking at the graph. We show the graph of y is equal to 3x plus 2, and we know that the limit as x approaches 1 of f of x is equal to 5. So we are interested when the absolute value of f of x minus L, which is our limit, is less than 0.01. Which means that we draw horizontal lines at 5 plus 0.01 and 5 minus 0.01, or 5.01 and 4.99. We then draw our horizontal lines over to the graph and then down to the x-axis. And we get two values on the x-axis, 1 plus delta, 1 minus delta. We are interested in that value of delta. To do this, we plug in what we know. You are told that the absolute value of f of x minus L is less than 0.01, when the absolute value of x minus 1 is less than delta. So f of x is 3x plus 2, so the absolute value of 3x plus 2 minus the limit, which is 5, has to be less than 0.01 when the absolute value of x minus 1 is less than delta. We work the left side and we get the absolute value of 3x minus 3 is less than 0.01, which means that 3 absolute value of x minus 1 is less than 0.01. Therefore, the absolute value of x minus 1 has to be less than 0.01 over 3, or the absolute value of x minus 1 has to be less than 1/300. So therefore, if epsilon is a number less than 0.01, that means that delta must be less than 1/300. That means that if we are within 1/100th of the limit of f of x as x approaches 1, our corresponding value of x must be within 1/300th of 1. This must seem like a very strange process. Here's an analogy that explains it. You are filling up a pool with water and would like to fill it to a height of 48 inches. The function that describes the height of the water over a period of X hours is shown in the figure. We show the line at 48 going over to the function and then down to the x-axis, which is the number of hours necessary to fill the pool to exactly 48 inches. Because of water sloshing in the pool, we place water sensors at 44 inches and 52 inches high. And if these sensors get wet, that is a signal to turn the water off. So we draw the horizontal lines at 44 and 52, and therefore our epsilon is equal to 4. That means that there will be corresponding values of delta. If the water height is greater than x minus delta L, or less than x plus delta R, the filling process stops. If we want more accuracy, then we can place our sensors 2 inches above and below 48 inches at 46 and 50 inches high. Doing that will give a corresponding value of delta L and delta R shown in green. The smaller the value of epsilon, which is the distance from 48 where we place our sensor, the smaller the values of delta. Number 2 reads, let f of x equals negative 6 minus x over 4, and L equals the limit as x approaches negative 4 of f of x. We want to find the positive value of delta such that the absolute value of f of x minus L is less than 0.1 when the absolute value of x plus 4 is less than delta. What this asks for is this. For f of x to be within 1/10 of its limit of negative 5 at x equals negative 4, how close must x be to negative 4? We see this graphically. The graph of f of x is in blue, and its limit as x approaches negative 4 is negative 5. If f of x is within 1/10 of negative 5, between negative 5.1 and negative 4.9, as shown by the red horizontal lines, how close must x be to negative 4, as shown by the red vertical lines? The trick to this type of problem is this. Once you set up your absolute value equation expression with the given value of epsilon, then change that expression, usually by factoring, to make it look like the absolute value equation expression with delta. So we look at the absolute value of f of x plus the limit as x approaches negative 4, which is negative 5, has to be less than 0.1 when the absolute value of x plus 4 is less than delta. Plugging in the limit and the function, we get negative 6 minus x over 4 plus 5 is less than 0.1 when the absolute value of x plus 4 is less than delta. Doing the arithmetic, we get the absolute value of negative 1 minus x over 4 is less than 0.1. We can take out the negative 1 because this is in the absolute value sign and write this as the absolute value of x over 4 plus 1 is less than 0.1. And we can now factor out a 1/4. So we get 1/4, the absolute value of x plus 4 is less than 0.1. We now have our absolute value of x plus 4. We need to get rid of the 1/4, so we multiply both sides by 4. So the absolute value of x plus 4 is less than 4 times 0.1, meaning that the absolute value of x plus 4 is less than 0.4. So if epsilon is less than 0.1, then our corresponding delta must be less than 0.4, meaning that if we are within 1/10 of the limit of f of x as x approaches -4, which is -5, our corresponding x must be within 4/10 of -4. In this problem, the delta value is greater than the epsilon value, as opposed to the previous problem where it was less. This is verified by our graph. Number 3 reads, let f of x equal x squared, and L equals the limit as x approaches 2 of f of x. We want to find a positive value of delta such that the absolute value of f of x minus L is less than 1/4 when the absolute value of x minus 2 is less than delta. What this notation-riddled expression is really asking for is this. For f of x to be within 1/4 of 4, how close must x be to 2? We're going to handle this problem graphically. We will graph 4 functions. y1 equals x squared, y2 equals 4, y3 equals 4 minus our epsilon, or 4 minus 0.25, and y4 is 4 plus our epsilon, or 4 plus 0.25. We want to show this in a window that will show the correct values of x and the correct values of y. So we will use an x-min of 1.5 and x-max of 2.5 as we want to be around 2. And for y-min and y-max, we'll use 3 and 5 as we want to straddle 4. And we can see the graph running through the 3 lines, 3.75, 4, and 4.25. We next find the intersection of our line y equals 3.75 with our graph y equals x squared, and we get x is equal to 1.936. We are interested in the absolute value of x minus 2 because we want to find how close this value of x is to 2. So we look at the absolute value of x minus 2 and we get 0.0638. We do the same with the line y equals 4.25 and the graph y equals x squared. Finding the intersection, we get x is equal to 2.0615. And again, we look at the absolute value of x minus 2, and we get 0.06155. To guarantee that the absolute value of f of x minus L is less than epsilon, our delta must be the smaller of the two values found. So our delta is 0.062, accurate to 3 decimal places. In number 4, we are given 2 problems with limits as x approaches some number and a value of epsilon. We are to use our calculator and the limit definition to find the limit and then the value of theta given the value of epsilon. In 4a, we are given the limit as x approaches -2 of x to the 4th minus 16 over x plus 2, and our epsilon is equal to 0.5. The limit as x approaches -2 of x to the 4th minus 16 over x plus 2 is 32. We can find this by factorization and canceling, or we could use L'Hopital's rule. There is a hole in the curve, and we can see this if we graph the function and then graph y is equal to -32, y is equal to -32 minus epsilon, which is -31.5, and -32 plus epsilon, which is -32.5. We then find the intersection of our function with the lines negative 31.5 and negative 32.5. In each case, we get an x value and then calculate the absolute value of x plus 2. This will give us our delta values. On the left side, we get 0.02069, and on the right side, the absolute value of x plus 2 is 0.02098. We are interested in the smallest value, and therefore our delta for this problem is 0.02069. In B, we are given the limit as x approaches negative 1 of 3 raised to the x, and epsilon is equal to 0.1. We graph 3 raised to the x, and the value of the limit, which is 1/3, and we will use 0.333. We subtract 0.1 from the value and we add 0.1. So we graph 0.233 and 0.433 and show it in an appropriate window. We find the intersection of 3 raised to the x with 0.233 and 0.433, and at each point get the value of the absolute value of x plus 1. On the left side, we get 0.32596, and on the right side, 0.23811. We want the smaller of these values, so our delta is 0.23811. Note that 3 raised to the negative 1 is 1/3, not 0.333. So we would expect that our answer might be slightly off, and it is. Our true delta is 0.238814, and that would round to 0.239.